In this section, we're going to look at two special cases when it comes to probability. First, we're going to consider the probability of at least one thing occurring, and then we're going to consider conditional probability in a little more detail than we already have. First note, the complement of at least one is none. So for example, if our event was having at least one girl in 8 births, then the complement is having no girls in 8 births, or in other words, having all boys. Similarly, the complement of none is at least 1. So if our event was rolling no 5s on 6 rolls of a die, then the complement is rolling at least 1 5 on 6 rolls. Suppose we flip 3 coins, and we want to find the probability of getting at least one tail. We could count up all the different possibilities. So for example, we would count this possibility, a tail, a head, because it has at least one tail in it. Whereas we wouldn't count a head, and then another head, because it has no tails. So we could just count up all the different possibilities and divide it by the total number of possible simple events in our sample space using the classical approach to probability, but we have a better way. That is to use this formula. It says the probability of getting at least one tail is the same thing as 1 minus the probability of getting no tails. So it seems at first, why would we bother with the probability of none? But occasionally, finding the probability of none is easier to find than the probability of at least one directly. So we can find the probability of none minus that probability to find the probability of at least one. So let's consider the probability of none first. That would be the same thing as saying the probability of the first flip not being a tail, and then the second flip not being a tail, and then the third flip not being a tail. But of course, each of those flips would be independent, so the probability of each of those occurring, the probability of none would be the probability of the first flip not being a tail times the probability of the second flip not being a tail times the third flip not being a tail. We can multiply those probabilities together because these are independent events. So of course that is 1/2 times 1/2 times 1/2, or 1/2 to the third power, which gives us 1/8 probability of no tails. And this intuitively might be obvious because that is the same thing as saying the probability of all of them being heads should be 1/8. There's only 1 out of 8 ways for that to occur. So to find the probability of at least one tail, we just have to subtract 1 minus the probability of no tails, or 1 minus 1/8, which gets us a probability of 7/8. The probability of getting a defective Firestone tire is 0.0003. If America's Tire Company sells 100 tires, what is the probability that they sell at least one that is defective? We'll let A be the event that at least one of the 100 tires is defective. Then A bar, or A complement, is the event of not getting at least one defective tire, or in other words, all 100 tires are good. Well, if we consider the probability of A complement, that would be 100 independent events where we're selecting tires and getting a good tire. So the probability of A complement would be the probability that the first one is good, which of course is 1 minus 0.0003. In other words, we look at the probability that any tire is defective. Well, 1 minus that will be the probability that we choose a good tire. But we want to do this 100 times since we're choosing 100 tires. So this is really the probability of A complement equals 0.9997 to the 100th power. And plugging that into the calculator gets us approximately 0.97. So that is the probability of getting 100 not defective tires, or 100 good tires, is 0.97. Well, then we can use the formula that we know about the probability of at least one defective tire is 1 minus the probability that none are defective that we just found, equals 1 minus 0.97, or 0.03. Conditional probability. The probability that an event B occurs given the added information that A has already occurred. So we use the notation probability of B, vertical line A, and we read this as probability of B given A. We have a formula for that that says the probability that the probability of B given A is the same thing as finding the probability of A and B both occurring divided by the probability that A has occurred. Consider the table of data regarding the polygraph information that we had seen previously. Find the probability of picking a subject who actually lied. Well, this is a simple case of where we just have to count up the people who actually lied, that is the 42 plus the 9, and divide that by the total number of people in this survey, 98. So 9 plus 42 is 51, divided by 98 is 0.5204. Suppose now that we had added information. So we want to find the probability of picking a subject who actually lied, given that we know the polygraph said they didn't lie. Well, let's label our events now. I'm going to label the information that we now know, that is the polygraph said they didn't lie. I'm going to label that as event A. And the event that we pick a subject who actually lied, I'm going to call B, event B. If we want to know the probability of B given A, we're going to use our formula. So let's first find the probability that A and B occurred. That is, the probability we pick a subject who lied, who is also one of the subjects the polygraph said they didn't lie. Well, of course, that's going to be the 9 people who are in the did actually lie column, but in the polygraph said they didn't lie row. So the probability that A and B occurs is 9 over 98. Or rather, the probability we choose someone who actually lied and the polygraph said they didn't lie are the 9 people in the did actually lie column and the polygraph said they didn't lie row. So now let's figure out the probability of A, and we'll plug all this into our formula. The probability of A, probability that the polygraph said they didn't lie. This is the 32 and the 9 people in the bottom row. So plugging this into the calculator, we get a probability of 0.4184. And now we can throw this into our conditional probability formula. And we get the probability of picking a subject who actually lied, given that we know that the polygraph said they didn't lie, is 0.2194. Be careful when you're talking about the conditional probabilities. It turns out the probability of B given A does not equal the probability of A given B.